Hey guys, welcome back to AlgoYogi. Today is a really special day because we are starting a complete new series, which is Stack. Although, meanwhile, I'm also working on a dynamic programming series, but it's going to be a long one, and I don't want to just post one video or like two videos or few videos. I will post it as an entire series, but meanwhile it's important to basically solve one problem each day. So I've started this series on the side. At the same time, I'm working on the dynamic programming series. Now let's start with Stack. Stack is a really important data structure, and very often problems are asked from this, and the combination of array, string, hashing as well. All right, so we're going to start easy. There are 9 easy problems and there are 18 medium level problems. So there are total 26 problems that we will be solving. 26 or 25? 25 problems. Okay. Yeah, so let's start with crawler log folder. That is an easy problem. That's our very first Stack problem, and there couldn't have been a better problem to introduce Stack. Honestly, like, I really loved this problem and I solved it. Okay, so let's go through the description. Though for a easy level problem, it seems like quite a lot of line of description, but trust me, it's as easy as Stack to understand, as a data structure. So the LeetCode file system keeps a log each time some user performs a change folder operation. Change folder operation, basically you're in a folder, you try to go into more folders or come out to the parent folder. So the operations are described below. So basically // you already know that. That's basically an operation that we use to basically, when you are doing operations in Linux, or like command line operator, when you're typing // and then you hit enter, it brings you to the parent folder. If you are basically performing this operation, // basically keeps you in the same folder, right? And then if you have a folder and then /, that means it's going to take you inside the X folder. So whatever I said, that's the exact same thing the problem has said. Now we are given a list of string logs right here. I guess you can't see it right now, but this is what I was trying to show you guys. Right now we are shown these logs, and these are the strings given in an array. These are representing as like operations, by the way. So what we need to do is you are given a list of strings logs where logs I is the operation performed by the user at ith step. So these are the steps that the user performed. Now the file system starts in the main folder, and then we're going to start with log I, basically log 1, log 2, log 3, something like that. Those operations we're going to perform. Now after we are done performing these operations, we need to return the minimum number of operations needed to go back to the main folder. So after you perform these logs, these operations in the logs, then basically this means that we are going inside D1, then we are going inside, now we are inside D1, then we're going inside D2, then we're coming out to D1 because it's this operation brings you back to the parent folder. Then you're going to D21 now, and then finally you are staying in D21. So you are basically, as you can see in this particular diagram here, we were in main folder, then we went to D1, then from D1 we went to D2, then we basically came out as a parent operation. This is basically brings you to the parent folder in D1, and then we went to D21, and then we stayed in D21 because this operation keeps you in the same folder. Now after we are done, if you see this last step, and I would at this point will switch to, all right, so I have written the logs, and that too, like at each step that we will be basically performing at the current state of our folder hierarchy. So in the beginning, as you can see here, we have this empty hierarchy, which means like we are in the main folder, right? And then once we perform this D1 /, that means we are going from main folder into D1, and then once we are in D1, we perform basically D2. So this is the state after performing this particular log. And then after basically performing .. that means we came out from D2 to D1 back, because this brings you back to basically your parent folder. Now this is our hierarchy, which is being in main folder, and then we have one nested D1 folder. And then this takes us from D1 to D21, and then this one you already know that it keeps you in the same folder that you are in. So what do you think is the data structure that we need to basically track these operations that we are performing, but maintains whatever basically hierarchy that took you to that particular step? So I think we are starting stack series, so definitely we're going to choose stack data structure to basically track it. And I think that I said it that this is one of the best problems to basically start data structure with, and let's find out why. Now, since this empty state right now we have this basically being in the main folder, is we're going to have our stack data structure, and this represents basically being in main folder. So this is our main folder, being like if your stack is empty, that means you are in main folder. You don't need to do any steps to go basically in or out anything. If this is your state, that means you return 0 number of operations to come to main folder. But then we have to go through all these logs first, right? So we're gonna go through these logs and we will perform these operations. So there are basically 3 operations that I'm seeing. One is there are 3 operations that I see, 3 operations that I can see. First is if you come to the parent folder, which is represented by .. Second is basically being in the same folder, which is this. And third is the most important one, which is some name and then slash. So this should take you to a folder inside the current state. Okay, so this is what happens on the log 0, which is over here. So 0, 1, 2, 3, and 4. Log 0 takes you to D1 folder. So what do? We will basically add this to our stack, right? Our stack. Okay, let me not draw the line here. So because we will be popping out these folders. So we are in D1 now. So this is my state. This is my current state over here. Then from D1 I go to D2 because that's my next operation. So I'll go to D2, and then third operation is basically coming out from D2 to D1, which is its parent. So I will pop off D2. Now my current state is again this. So if you see my step 0 and step 2, they're basically representing the same state, and that is why we needed a stack, so that we can, if we are performing this particular operation, which is bringing you to your parent folder, that means you need to pop off this current state and come back to the old state. Now if you see in step 3, we are basically going from D1 to D21. So we will again it's called pushing in stack operation, but I'll be using an array to basically perform these operations: push, pull, push, pop, and I think one is peek. So these are the 3 operations in stack. We will come across these when we are doing an implementation one. I think those are the main operations of stack. I should have started the video like that, but I'm assuming that you already are familiar with stack operations, so which is push, pop, peek. Okay, so this is like pushing. So right now from D1 we came to this particular state, so D21. Now when we were here at our 4th step, we performed this particular step, which is staying in that current folder. Now if you see in my stack, the length of my stack is 2, and that is the number of operations, minimum operations to get to get to main again. Main, what was main? Number of operations to get to main. Main was just empty stack. So the operations that are available right now are these. I have these 3 operations available. One is going back to the parent folder, another one staying in the folder, or going to another folder, from the current folder. So I think to come back, I need this particular operation. This is my main operation to basically come out of some folder to keep going back so that I can reach the main folder. So I will be first popping this off by performing one of this operation, and then this will be my state, and from there again I will be basically performing another of this operation, and that should take me to an empty stack, and that's where I will basically be in the main folder. And length, basically I don't have to perform these operations, but I'm just saying that the length of this stack would be the number of minimum operation that we need to perform to basically go back to the main folder. Okay, so I'm gonna leave us here, and then let's implement. This will be a big of n time complexity solution, and space will also be big of n. N is the number of logs or steps that we will be performing. So first thing first, let's have a stack. Stack in Python is an implemented data structure as well, but since we are like in a technical interview, we need to implement our own stack, or we don't need to always, but like in this it does make sense. In Python, definitely. Okay, so we have a stack, and then for log we will be going through the log. For log in logs, if my current log is equals to this particular symbol, that means I need to return to my parent folder from here, but only if stack is not empty. So if stack, that means we are not in the main folder. If you're in the main folder, then you don't need to do anything. But if you're not in the main folder, and you will not be in main folder if stack has something inside it, and you'll know why. So if this is the case, then we just basically pop stack.pop, so which will take us to the main, to one level up, basically from the current folder to its parent folder. Else if we have the symbol this one, so that means we stay in the same folder. Else, that means we have seen some log that takes you inside another the current folder to the folder that it's seeing right now, log. So we will basically append that to our stack. So stack.append. These are the 3 main operations. So append here is basically push operation, and pop is pop, and then peek is like we're not using it, but usually peek could be this operation. So I'll just write it for us, because this is the very first stack problem, so I just want to write it. So peek would be, in our case, this operation, basically stack -1, only if otherwise, like, it will return nothing. So this is like checking the last element, because we are pushing the element from the back. Okay, now what do? We return the length of stack. Okay, and the reason is because that's the number of minimum operation that will take us to come to the main folder, right? Because we can only take in one step, max we can do is just come out of that particular to the main folder. But in general scenario, if you just write cd current directory in regular, while you're coding, if you write cd and this just enter, I think that also brings you back to the main folder. Just cd, don't type anything, cd current directory something, no, just cd, enter, takes you to the main folder. Okay, now let's zoom out and run it on the example. And did we forget something? Oh yeah, we need to append the logs. Oh my god, I think it's the glasses. No, it's not the glasses. What is it? If log is equals to okay, I don't have to like re-record because I was in the flow. Now I'm gonna submit it. Yeah, sometimes you keep feeling that I need to re-record, but you know why? You made the mistake you made. Like I did make a mistake in the very first problem. I hope I didn't. But anyway, who cares? We are learning right now. You should make the mistake while learning and not while interviewing. I will try not to. Okay, time complexity would be big of n, because where n is the number of logs, because we are going through these logs, and at max space complexity worst case would be big of n as well, and that is because this stack, let's say if we never saw this particular operation, and only we just keep going this nested hierarchy, folder, right? Sometimes when you're trying to find logs, you just keep going through into the these nested folders, then the worst space-time complexity would be big of n. All right, then let's go back to AlgoYogi and mark this solved. I think we still have that problem. Okay, I think I'm gonna fix that and deploy these changes. Until then, bye bye. See you guys later. Ooh.